Okay, so now we're going to do the second part of this analysis, which will be the 5 regen channel simulation. So we're going to go back to fluid flow fluid, and we're going to drag this and create a standalone system right underneath our annulus simulation. We're going to double click on geometry and open up discovery. Okay, once Ansys discovery goes up, we're going to follow the previous step. We're going to insert geometry. We're going to go select our regen channels. Okay, so once our 5 section regen channels are imported, we're going to follow similar steps as of before, where we're going to go up to prepare, we're going to go to volume extract, and then we're going to select the surfaces which enclose the internal volume. So we're going to select the inlet to the annulus, we're going to select both sides of the cutouts, and then we're going to select the top flange. And then after that, we're going to come over here and we're going to select a interior face of the enclosed volume, and then we can select create. So now we can see the volume that has been created here. I would inspect this to make sure that there's nothing funny going on or nothing incorrect. Okay, so when that's done, the last thing that we want to make sure before we go into Ansys Mechanical is we want our coordinate system to start at the top flange. So to make that happen, we can go over here, we can select both of our fluid volume and our solid, and then we can go over to design, and we can select move, and then we can move this by the same amount as specified in our RPA data. So we can see here that our chamber is 327.4 millimeters long, and we can see that our axis starts right at the end of our chamber. So then we need to move our solid down by 327.4 millimeters. So we can click right here, and then we can type in 327.4. Okay. And then we can click away, and now we see that our coordinate system starts right at the very, very top of this flange, and our positive y direction points down. So after this is done, we are done with Ansys discovery. We can come back to our workbench and we can select mesh. Okay, so the first thing that we're going to do is we're going to come over to geometry and we're going to create our name sections for our solid and fluid volume. So you can right click on the geometry, go to create name selection, and we're going to call this one solid volume. We're going to call this one fluid volume. And then we're going to specify our inlet and our outlet. So we can select face, go over here, right click, create name selection. We'll call this inlet. And then at the top of the regen channels, we're going to select one regen channel, right click, go create name selection, select apply geometry items of same size, and then we're going to call this outlet. Okay, and then we're going to select all the interior chamber walls. So we'll press Control and then select all of the interior faces of the chamber. Right click on them and select Create Name Selection. We'll call this Chamber Walls. Okay, lastly, we need to select the regen channel wall. So we'll come over to the solid volume and select Hide Body. And then we will select all 4 sides of one of these regen channels. Using the face select tool, we're going to right click, create name selection, apply the same geometry, apply the geometry of same size, and we're going to call these regen channel walls. Okay, after that, let's go over to name selection. Let's make sure that we have everything defined. We can see that our inlet is defined, our outlet is defined, our chamber walls, our regen channel walls is defined, and then our chamber walls is defined. Okay, so after we have the name selection done, we can go over to connections and make sure that our contact region is correct. Here we can see that our target body is the fluid volume and our contact body is the solid volume. We can see that the contact regions are correct. Okay, so after we're done creating our name selections, we can go ahead and create our mesh. Creating the mesh for this model is very, very simple. We're going to right click on mesh, we're going to go to insert and then sizing. We're only going to use one sizing method for this whole mesh. We're going to go switch from geometry selection to name selection, and then we're going to select our regen channel walls. We're going to change the element size to 0.3 millimeters, so 0.0003 meters. And then right when that's done, we can right click on mesh and click generate mesh. This mesh will take quite a while to generate. Okay, so that took about 10 minutes and the mesh is now done. We can see that it is quite fine, but that is for a good reason. It needs to be this fine. The first thing that we're going to do is evaluate the mesh quality of the fluid volume. So we can go and hide the body of the solid volume. We can go click back on mesh. And we're going to be looking for pretty much any sort of weird discrepancies with the mesh or areas where the mesh isn't very fine or needs more refinement. Say most of these regen channels look pretty good, decent, but just take a look all up and down them and make sure that nothing weird is going on. And then the other place that we want to look is where the mesh intersects with the annulus. We can see that the mesh is fine, it still is quite fine near the end of the regen channel and slowly becomes more coarse as we move away. That is perfectly fine. We just want to make sure that we still do have a refined mesh towards the inlet on the annulus. And all that looks pretty good. The next thing we're going to want to check is we can then check the solid mesh. And you may ask yourself, why does the solid mesh need to be this fine? You know, considering basically all we're doing is transferring heat through it for this Ansys simulation. And the reason for that is the heat flux loads, especially on the throat, are so incredibly high that if we have a coarse mesh, individual nodes will be hotspots and they won't distribute their heat well to the regen channel. So the inside of the thrust chamber and the regen channels need to match their meshes or match their the refinement and the fineness of their meshes. And so that's what we've done here, and that's why this simulation is so computationally intensive. But yeah, this mesh works. Sometimes if you generate this mesh and you see that the solid portion is very, very coarse, likely something's messed up. I would not continue. It will not work. It's possible that part of your regen channel is poking out through the mesh. And yeah, if that happens, you may have to go back to your CAD model and make sure that no part of your regen channel that you're modeling is poking out of your solid body. And then right after this, we can go straight back into our workbench and we can click Update Mesh. And then we can double click Setup. So once we launch the fluid launcher again, click double precision and use as many cores as you can. And then we can press start. Okay, so once our model is imported, we can see that the inlet and the outlet have already been assigned because we used the name selection to name them inlet and outlet. Make sure that under solver type, we're using a pressure-based solver, an absolute velocity formulation, and a solving for a steady state time. Next, we're going to go up to physics. We're going to click energy to activate the energy equation, and then we're going to make sure that we're using the K omega viscous model. After that, we're going to add our materials again. So for the fluid, we're going to go to Fluid Database. We're going to go down and we're going to find Jet A. Okay, so then we're going to add our fluid. So go to Fluid Database, scroll down until you find Jet A. Here is Jet A liquid, and then we're going to change the properties so that they are a function of temperature. And then we can press copy. And then we're going to go add our solid. We're going to go to the Granta MDS database, select solid, and then go all the way down till we find copper C 18200. And then press copy. And then close, close, close. Okay, then we're going to go to cell zones. We're going to select fluid volume. And we're going to select Jet A as the fluid that we're flowing through this fluid volume. Press apply, press close, and then we're going to go to solid volume, and we're going to edit the material that the solid volume is made out of. We're going to select copper alloy, and then we're going to select close. Then we can go to boundaries. We're going to change pretty much the same boundaries that we did last time. So we care about the heat flux in the chamber wall. We care about the inside surface roughness of all the fluid volume walls. And then we care about the inlet and the outlet conditions. So let's start with the inlet conditions. So thermal is going to start at 300 Kelvin. The initial temperature is going to be 675 psi, which is 4.65 megapascals, so 4.65 E6 pascals. And then the velocity magnitude, so here we're only running 5 regen channels. So we basically need to take our past velocity, okay, and divide it by however many regen channels are in the total TCA. So there's 45 regen channels in the total TCA for this model. And then we're going to multiply that by how many regen channels we're testing, which is 5. And we get a inlet velocity of 0.6385. We'll take another digit there too. Okay, so then now we have the velocity magnitude at the inlet, and we can click apply. Okay, now to the outlet. The outlet back pressure is going to be 4.35 megapascals, or 4.35 times 10 to the power of 6 pascals. And then the backflow temperature is going to be 550 Kelvin. After that, we can press apply, and we can press close. Next, we're going to go to the chamber walls, and we're going to add our heat flux. Okay, so now we're going to add the heat flux load. To do that, we're going to create an expression. So come over here to heat flux, go down to new expression, and then we can name this expression chamber heat flux. There we go. And then to create this expression, we're going to come over and we're going to use our RPA data that we previously used, and we're going to use ChatGPT. So first, let's go over the Ansys Fluent Expression Dump. This is where I'm dumping all of the expressions that I have built thus far, so that in the future, if we want to use them, it's super duper easy to just copy and paste them over. So for example, if we're running, like 6 different cases with the 1.6 V1.6 model, right, we can just collectively all use this exact expression without having to regenerate them. In order to generate these expressions, we can use this ChatGPT prompt. So if we come over to ChatGPT and we select new prompt, we can then select all of this data right here, copy that over, and then paste it right below. And then sometimes, occasionally, it helps to also include an example of a previous expression that works. So you don't have to do this, but it does help, in my opinion, ChatGPT get on the right track. You can just write an example of the expression is, and then you can just take a previous expression that has worked. Only put expressions in here once they've worked, by the way, and then I'll show you where to get these graphs from. Then you can just paste that right below. And now ChatGPT has an example, it has all the new data, and it has a good prompt that I know works well. After that, you can just submit all that and let ChatGPT think about it for a couple minutes and get back to you with that expression. Okay, looks like Ansys has spit out our new expression, and we can just go over to copy code. And then we can go to Ansys Fluent. We will have to remove this up here just fine. But we can see it works. And then we can select the maximum of 0. Let's do like 3, 4, I think. And we can see the plot of this expression over time. So we can then go copy to clipboard, and we can paste this in the dump. So let's paste that right there. Let's change this. And boom. So now we have another expression in here that we know works. And anytime you want to use this in the future, you can just come back here and copy this over into your Ansys simulation. Okay. So now we can see that this looks pretty good. This does like approximate the data really, really well. If you want to compare it to RPA, you can go over here, go to results, go to thermal analysis, press plot temperature. In this case, we want to plot heat flux. And we can see that, it matches pretty damn well. It comes up, it's pretty much straight. It's, spikes near the throat to, roughly a little above 10,000 kilowatts per meter squared, which is correct, and then it goes all the way back down. Okay, so then after that, we can press OK. And then we have our chamber heat flux equation in there, and everything else should be good. We will change the material to our copper alloy too, and press apply. And then after that, we press close. Okay, perfect. So we've done the inlet, the outlet, we've done the chamber walls. Now we need to define the surface roughness of the inside shape. So we have this wall fluid volume that we can edit. And we're going to put a roughness of 100 microns, which is 1e negative 4 meters, 0.1 millimeters. And we can select apply and then close. And then we also want to look at the contact regions here. So wall 18 of the target, and then wall 17. So wall 17 and 18, we also want to change the surface roughness of. And then wall 18. Okay, so now our chamber wall is done, our inlet is done, our outlet is done, and all of our surface roughnesses for the inside of our fluid volume is done. So that concludes pretty much all of the boundary conditions that we have to do. So after that, we can go down to methods, and I'm just going to come here to show you that I'm just using the standard methods of whatever Ansys Fluent comes up with. And then we can go to controls, and let's go to report definitions next. So the first report we're going to make is going to be our mass flow rate report coming out of the outlet. This is just so we can monitor continuity and make sure that the inlet mass flow rate matches the outlet mass flow rate, and this will help us monitor the convergence. Next, we're going to do a surface facet average report, and we're going to take the temperature of the outlet. So this was going to compute the average temperature across the surface area of the outlet, and this is going to tell us basically what the temperature of the jet A is coming out of the regen channels. This is also really, really useful for just kind of giving us a ballpark estimate for what is going to be the temperature of our jet A coming out of the regen channels. And we can also see like if it's too low or too high, or, you know, obviously if we get like a number that's like less than 300 Kelvin, we know we messed up. But also if it's not somewhere around, like RPA says it'll be around 500 Kelvin, if it's significantly above or below that, we know we probably messed up somewhere. So yeah, after we select the field variables temperature and the outlet, we can press OK, and then we can close. The next thing we want to do that we forgot to do earlier was check the mesh. And then we're going to come down to initialization. We can select hybrid initialization and then select initialize. So once hybrid initialization completes, we can go down to run calculation. We can select our number of iterations as 500. And then let's check case. So this will come up. So minimum orthogonal quantity is less than 0.01. Consider trying to improve the mesh quality before proceeding with your simulation. This will come up because the aspect ratio of the fluid volume that we were simulating is so high. So basically our fluid volume is very, very thin and very, very long. You know, obviously if we make our mesh any more fine than it already is, it's going to be extremely computationally intensive. So, you know, that is something that you will see, but I don't think that you should have to be like specifically super worried about this at the moment. And then once you're ready, you could just press calculate, and you can wait about 6 to 8 hours, 6 to 12 hours, depending on how powerful your computer is, to get your results. Okay, after the simulation finishes running, we can look at the residuals. We want to make sure that the continuity residual is basically that we see it's to the power of -3. And we want to make sure that all of our other residuals are pretty much at least to the power of -3, which they all are. This is probably still a little bit higher than we want. We may want to in the future decide to be below 1 to the power of -3. But for now, this is the best result that we've had so far. Generally, if we're both below like 3 to the power of -3, I'm probably going to be pretty happy, which we are here. Next, we can go over to one of our reports, and we can see the temperature of the coolant leaving the outlet as a function of the number of iterations. So we can see it's steady right around 500 degrees Kelvin, which is right where it says we should be according to RPA. And then we have our mass flow rate versus iteration, which pretty much just stayed constant. Okay, the next thing that we're going to want to do is we can come down to graphics, and then we can go to contours. Double click on contours, and the first contour that we're going to do is the static temperature contour. So go to contours of temperature, static temperature, and then select every single surface here. Then we can just press save/display. And this is going to show us the static temperature of the outside walls of the TCA section. So we can see we actually do have this hotspot right along this corner. That's likely because this corner is not able to transfer heat well to the regen channels, probably because this would normally be in the domain of the next regen channel over. That is okay. Generally speaking, we want to look at the middle values here. We can also see this side is a little bit cooler for the exact opposite reason. This side's probably a little bit closer to the closest regen channel being modeled. But that's okay because we really just care about the average across here. And we can see that for most of the chamber, it stays roughly the same temperature. We do see a little spike at the throat, but it's not unreasonable. And then obviously the nozzle is perfectly fine. We can also see how the heat is transferring through the wall. We can see that the back side of the wall is significantly cooler than the chamber side of the wall, which means obviously our coolant is doing a lot of heat dissipation for us. So we will get a couple images here of this model. So you can orient this along the z-axis. You can use these arrows to turn it right side up. And this will be the first screen grab that you'll get. We can also adjust this range by clicking on it. And we're going to set the maximum temperature to 1000 Kelvin. And then the minimum temperature to 300 Kelvin. We're going to do this range for every single model that we do. That way we have a constant, basically thermal gradient to compare all of our models of when we have images of them. And then there we go. We can take an image there. We can also take an image from the top and perhaps one of the inside of the thrust chamber the other way. Like right there. The next one that we're going to go do is we're going to go find the temperature of the regen channels. So we can unselect the contact region SRC and the regen channel wall contact region SRC, and then we'll unselect all of the walls and press save/display. This will display just our regen channels. So now we can just see the temperature of our regen channel. Okay, so after we're done with static temperature, we're going to go to static pressure. So we can go to contours of pressure, static pressure, and then we want to unselect all of our walls and unselect the SCR, which is the solid faces in the regen channels and in the fuel annulus. And then, so now we're only selecting the fluid walls, basically. After that, we press save/display. And now we can see our static pressure. And then we're going to want to get another image of this right here. There we go. And we can see that the pressure here exceeded our original input pressure. So our original input pressure was 4.65 megapascals. Yet the new input pressure, according to this, is 4.78 megapascals. This means that roughly we increased, 0.13 megapascals. So pretty much what this means is that the pressure drop through the regen channels was higher than we initially estimated. That's perfectly fine. In fact, in this case, it's a good thing because now we know exactly what the pressure drop is. If you convert this range to PSI, this is 63 PSI difference in pressure, which is actually right around where we want to be. We want to be, somewhere probably above 45, somewhere below like 70. So after this one, we're going to go find the wall function heat transfer coefficient. So go down to wall fluxes and then select wall function heat transfer coefficient. We're going to keep the same surfaces selected. And then this is going to show us our film coefficient. And so we will need a couple more screen grabs here. We notice that obviously our film coefficient is highest right along the center of the regen channels, where the regen channels get the smallest and the velocity gets the highest. Also, as the fluid comes around this bend here, it kind of impinges itself on the inside of the regen channels, which further promotes cooling. And then we can see, obviously, the film coefficient levels off towards the end and at the beginning of the regen channels. Okay, and for this one, we will adjust our range again. This time, we're going to set the maximum to 20,000. And we will get a screen grab right here, too. Okay, the next one that we're going to do is we're going to do this total surface heat flux. This is just to make sure that we set our boundary conditions correct. So if we go to total surface heat flux, and we're also going to select all of our walls. Okay, so this is the actual surface heat flux that we set on the surface of the inside of our chamber. And we just want to make sure that it looks correct, right? Obviously, we see the highest heating at the throat, and then after the throat, it levels off. And then we see pretty medium heating in the chamber, and at the top near the injector, the heat flux lowers. And we don't need an image of this. We're just taking a look to make sure that everything looks correct. Okay, after that, we're going to go back to our workbench. Okay, so after that, we're going to go back to the results tab, and in the results tab, we'll be able to do the rest of our visualization of our analysis. Okay, so just like before, we're going to set up a couple different analyses. So the first one that we'll do is we can click on Streamline, and 3D Streamline, we can select all domains. We can say start from inlet, equally spaced, do 200 points, and then click variable velocity. After we click apply, we can see our velocity streamlines here. So here we see the velocity increase in the middle at the throat of the regen channels. Obviously the velocity is the lowest at the inlet. That is all right what we would expect pretty much. And so we'll grab another image of this right here. And the last image that we're going to grab is the volume rendering. So for the temperature volume rendering, we're going to select all domains, temperature, local range, create a resolution of 100 and a transparency of 0.5. And this will allow us to kind of see through the brush chamber walls a little bit to see how that heat flux is interacting with the regen channels. And we'll get a couple screen grabs, we'll get a couple screenshots of here to submit in each analysis that we do. There's one more that may be useful, and that's the vector of velocity. So here we can select vector right up here, and then we can select all domains, fluid volume, and then a factor of 1, and we're going to select velocity as the variable that we care about. This will show us a couple interesting things. First of all, we can see the velocity vectors at the inlet, and we can see how they're, kind of all over the place before, we enter the regen channels. And we can also see things like how the swirl of the helix angle affects the velocity throughout the regen channel. So on this side, we see that the velocity is higher on one side than it is the other. This is actually a good thing in our case because the velocity is higher on the side of the chamber, which means the film coefficient is going to be higher on the side of the chamber. And that's because as this fluid comes and it swirls around this throat, pretty much it impinges itself on the throat, right? So you can think about this like it is, let me orient myself here. The fluid is coming in at an angle, right? And then it's kind of moving inwards radially at the same time. And then right at the throat, it decides to move outwards radially again. And that kind of is like forcing the fluid against the wall of the throat, which is a good thing in our case. So this is also not a bad screen grab to get, or not a grab, or no. This is also a good thing to screenshot. Okay, so in the next video, we're going to add a static structural analysis, and we're going to import our thermal data and our pressure data from Fluent and see how this holds up in structural analysis. But this is pretty much all the analysis that we're going to do for CFD. So anytime we need to do CFD analysis, on a new model, this is pretty much the exact procedure that we're going to